Okay, looks like we're ready to get going. Thanks everybody for dialing into the Transportation Infrastructure Precast Innovation Center Research Highlights webinar for March 2025. Really happy everybody could call in. We have two great presentations today for you, one from the University of Illinois and one from Purdue University. As with a webinar, the formatting, if anybody has questions for our presenters, please feel free to add them into the Q&A button at the bottom, and we'll be monitoring that as the presentations go. We probably will save the questions for the end of the presentations, and the presenters can read the Q&A and answer any of the questions that the group has. Lastly, I just wanted to note that it's a bit of housekeeping coming up. TRANS-IPIC, we're really proud that to be working with PCI in Wisconsin. We have our second annual workshop in Chicago coming up in just a few weeks, the 22nd, 23rd of April. We've got some great presentations. We have a quick tour lined up. If anybody's interested, we have a QR code there at the bottom if you'd like to scan. Also, please feel free to reach out to us if anybody has any questions. With that, I think we can roll right into the first presentation. We'll stop sharing my screen. So the first presenter we have is Professor Bassem Andrawes from the University of Illinois Urbana-Champaign. He holds a Bachelor of Science in Civil Engineering from Ain Shams University, a Master of Science in Civil Engineering Structures from Iowa State University, and a PhD in Civil Engineering Structures, again, from the Georgia Institute of Technology. He's been on the faculty of the Department of Civil and Environmental Engineering at the University of Illinois since the fall of 2006. And prior to coming to U of I, Professor Andrawes worked as a postdoctoral scholar at the University of California, Irvine, and as a design engineer at Engelkirk Partners Consulting Structural Engineers in Santa Ana, California. And lastly, Professor Andrawes is the director of the Transportation Infrastructure Precast Innovation Center. So really excited to have this presentation.
Thank you, Chris, so much for the introduction. I'm really happy to be with you all here today. Let me start by sharing my screen.
Looks great.
Okay, great. Thank you, Chris. Well, again, good afternoon, everyone. It's my pleasure to be with you here today. And as Chris mentioned, the title of my talk today is Metal with Memory, an Innovative Technology for Transportation Infrastructure. I'm sure some of you might be wondering about this title. It's a little bit unusual, but I'm hoping that maybe 20 minutes or 25 minutes from now, you will understand the reason behind selecting this title for my talk today. First, let me start by giving you a very brief idea about the motivation behind this work and why we're so excited about doing research about these new metal that I'm going to be talking with you about today. By the way, they are referred to as shape memory alloys, or abbreviated as SMAs. I'm going to try to give you a little bit, some quick overview of the main important features that excite us about these metals, namely the super elasticity and the shape memory effect. And rather than going in one particular application for my presentation, I chose here to go through like an overview of some samples of the work that we have been doing through TRANS-IPIC, especially here at the University of Illinois related to SMAs that would hopefully give you an idea about the potential of these new materials. And then I'm going to wrap up with the conclusions, of course. Starting with the motivation, well, really the motivation is the dire condition of our transportation infrastructure. So it's no secret that we are in need for reshaping the future of our infrastructure if we want things to be a little bit different a few decades down the road. The numbers highlighted here in red, those are just few examples of the condition that our infrastructure is suffering from. Therefore, we see like some buzzwords like resiliency, sustainability, energy efficiency, durability. These are all key words that are floating around us whenever we attend a meeting or a workshop or a conference, and they are very important keywords that we need to think about very, very carefully. We need to think about innovative ideas, technologies for the future. And of course, we can't just keep repeating the same technologies and expect the outcome to be different, 50 or 60 years from now. Therefore, we are thinking about new materials, and that's the area that I'm going to be focusing on today. If I ask you just simple question, what would be the most material you would say is being used in our infrastructure, transportation infrastructure? I'm sure most of you will say concrete and steel. And you're not wrong about that. You're absolutely right. However, these materials are great and they have served us well over the last century, even more. But it's not a secret that they have their own shortcomings and limitations. For example, concrete cracks in tension, steel corrodes. The concrete cracking even exacerbates the issue of steel corrosion. Steel yielding, some of us think of it as a blessing, which is a blessing surely for ductility, but when you think about the resiliency, it's actually against resilience by definition. Also, these materials are stiff, rigid. They lack versatility, adaptability to the surrounding environment, whether it's loading environment or even climate. Now we are becoming more and more even aware of the cost on the environment that producing these materials have. It's unfortunate that when we drive on our bridges here in the US and we see images like the one I'm showing here in this slide, we become numb to it. We could become used to it. It shouldn't be the case. And we should definitely strive for better outcome for our next generations and next generation of transportation infrastructure. Therefore, we started thinking about emerging and new materials like shape memory alloys. By the way, let me just declare here very early on in my presentation, we are not suggesting or proposing to replace existing reinforcement with these metals or these materials, but rather supplement these reinforcement with these materials. And hopefully the examples I'm going to be sharing with you today will highlight exactly what I mean by that. So when we say new metal or SMAs, if you see it, if you feel it, it looks like any other metal. However, the unique thing about it that if you deform it beyond its elastic range, the material can actually remember its original shape when subjected to temperature. If you haven't seen this in real life, I have this video here today with me that shows me stretching a spring made of SMA beyond its elastic range. You think it's permanently deformed. However, wait until you see what happens when I subject it to some heat through this flame. It immediately starts recovering its original shape. The thing about it is that it can do this over and over again, the same spring. So it's a repeatable process. SMAs are not new. They have been out there. They have been used on high-end fields for decades now. Fields like aerospace, biomedical, robotics. And they are becoming more now popular than ever when it comes to their availability commercially. They are found in the form of wires, bars, sheets. One important thing I want to point out here is that SMAs is not one type of material. It's actually a group or family of materials that exhibit more or less similar behaviors. For example, as you can see down here, we have the nickel titanium family, which is the nitinol comes from this family, the most popular commercially available alloy out in the market. And now we also have copper-based alloys, iron-based alloys, which really got civil engineering folks excited about using SMAs because they are more cost-effective. And our role here in civil engineering to choose the right alloy that would work, or alloys, I should say, that work for us in the civil engineering, applications from not only cost, but durability and resiliency as well. Let's just delve a little deeper into the mechanical properties of these materials. First, I want to say and make it very clear that when you say SMAs, you have to identify what type of SMA are you referring to. Is it superelastic or shape memory? And they are completely two distinct behaviors that cannot coexist, by the way. And I see sometimes confusion about these issues. So for example, when you look here at your left side of the slide, you see this nice flag shape hysteresis. That's the superelastic behavior. So you see here, there is like what looks like yielding point, there is a plateau, there is ductility, there is energy dissipation. But when you remove the load, the material bounces back and goes to zero strain, gives us this nice flag shape hysteresis. Some people refer to it as pseudoelasticity or superelasticity. I sometimes like to refer to it as nonlinear elasticity. Now we're used to the term linear elastic or nonlinear plastic. Nonlinear elastic is a little bit not very common to use, but this is actually what it is. And it has all the features from damping to self-centering to ductility that excites earthquake engineers and researchers to be studying it and using it. And that's what this is very popular for. So most of the studies out there, you will find it on that type of alloy for earthquake engineering application. The less studied one, but now there is actually growing interest in using it and applying it, is the one on the right here. You see it acting like any metal. It has the yielding point, it has the ductility, but when it unloads, it does that with very large residual deformation. However, like the spring I showed in the video earlier, it can remember its original shape if you subject it to some form of temperature. The great thing about this, though, is that if you subject it to that temperature while restraining it, it will pull back very strongly, trying actually to remember its shape. And that force developed during this pulling process is called the recovery force or the recovery stress. It really triggered in many minds the idea of using it for pre-stressing, thermal pre-stressing, without need for hydraulic jacking or any anchorage system. And that's the unique thing about this. And hopefully in the examples I'm going to be showing you today, you will understand what I mean by that. Going back to the superelasticity, for those who are not sure about the self-centering capability, what does this mean? This is a simple beam. We're subjecting it to bending. It has two SMA superelastic bars inside. Look at the crack forming in the middle. Well, that's expected, of course. But wait until you see when we remove the load, because it's cyclic loading, the crack will start closing. And that's what we mean by self-centering. The beam is actually having the ability to recover back to and bounce to its original shape. See how wide the crack opens? You think it's done, but see when the load is removed and watch the crack, it's closing. That's the beauty about the self-centering or recentering. And you also look here at the CMOD, that's the crack mouth opening displacement. It started taking that nice flag shape hysteresis. Eventually it failed in shear because we didn't actually plan to, design it to have shear reinforcement. But you got my point. So the self-centering have found its way in applications like in, rebars and plastic hinges for bridge piers, or in moment-resisting frames, or even bracings for seismic frames. And you will find a lot of research in that direction. Switching to the, as I said, a little bit less studied and less understood phenomena, which is the shape memory effect and how really it could be used for thermal pre-stressing. Let us start here with, for example, bridge piers. I'm showing few examples of issues that we have seen in the past, either during earthquakes or even issues with the construction of seismic structures, like with high steel congestion. A lot of these problems could be attributed one way or the other to the transverse reinforcement. Now, let me ask you this simple question. Can you imagine having a transverse reinforcement like a spiral, for example, or a strip inside a beam that is pre-stressed? How can you even start thinking about pre-stressing a spiral inside a column? Well, it's very difficult, and even if it's achievable, it's not a very simple process until we started thinking about the thermal pre-stressing that we can use for doing that. The process is very simple. We have pre-strained wires or bar made of SMA. It's delivered already to the site in the pre-strained condition. You form it as a spiral, you put it in the form, and you cast the concrete. When the concrete sets, you now can activate it by subjecting it to temperature. It will attempt to shrink, it will try to squeeze the concrete, and that squeezing effect, we call this lateral pre-stressing, transverse pre-stressing, or sometimes we refer to it as active confinement. So that is the unique thing about these materials. One could argue, how does active confinement really behave, or how does this differ from passive confinement, which is the conventional transverse reinforcement we're using? Well, I have this simple example here for you to compare both. We have two identical cylinders, identical in everything except that the wraps on the left are made of steel, basically, and the wraps on the right, this is like this SMA spiral. So I'm going to run both of them simultaneously here. We conducted a cyclic test, compressive test, basically loading, unloading. And I want you to start watching actually the progression of damage in both specimens. See here the shear diagonal cracks forming right away very quickly, and then boom, the fracture of the spiral. While when you look here, I want you to watch the plate on the bottom just compressing, squeezing like the concrete here and unsqueezing. It's like a pillow. So before your own eyes, you can see actually the concrete being squeezed. Only 2 millimeter diameter wire that you are able to wrap with one hand is able to do this to the concrete. By the way, this is not special concrete. It's just regular, normal 4 or 5 KSI concrete. The effect is significant. Of course, there is some effect on the strength, as you can see from this stress strain curve, but more importantly, the additional ultimate strain that we gained, which translates obviously to additional ductility. So we wanted to look into this more deeply into the column level. We have two columns, the one on the left wrapped with the SMA spiral, again, active confinement, the one on the right, passive confinement with glass fiber reinforced polymer. The FRP started well at the beginning. However, we started seeing early compression failures, crushing essentially of the concrete, and then what looks like an explosion at the plastic hinge of the columns. While the one on the left, no matter how much we push it, we even maxed the stroke capacity of the actuator and still didn't see any fracture of the spiral or crushing of the concrete. So that was an amazing amount of ductility that this column exhibited. Not only that, when we uncovered the columns and took all the wraps off and inspected the concrete underneath, for the case of the FRP column, almost half of the cross section was completely gone. It's unusable. While the one on the left, yes, there are damages, but it's in a much better shape, which will affect the post-earthquake functionality and the repairs, the downtime, and all this important stuff that decision makers and bridge owners have to make after an event like an earthquake, for example. Speaking of repairs, we started thinking about how about if we use these materials, not for even permanent repairs, but emergency, quick, even temporary repairs after events like earthquakes or hurricanes. Now we know that that will require a very quick act. So we wanted to test this in case you have a main shock hitting a bridge and then damaging it, and you are not sure should the bridge be kept open for even emergency vehicles, or should we just close it? So we wanted to test this concept with just these small SMA wires. So we had one of our bridge columns that were tested in our lab, severely damaged. Two of the rebars even were fractured. So we coupled it with actually two couplers here. We injected epoxy in the cracks. We applied fast-setting mortar, and then we wrapped it with SMA at the plastic hinge zone. And you see here my former student just applying, with a blowtorch, just heating it. In a matter of seconds, you see the spiral, even before your own eyes, attempting to squeeze the column and apply the confining pressure. So we wanted to test this concept under actual dynamic load effect. And the best way to do this is through a shake table test. That's actually the only way to do it right now in our labs. So we took one of the columns that were damaged, and again, the damage here is in the form of, cover spalling, exposure of the internal steel hoops. And we performed that repair process, and it took about 2.5 hours to complete that. And then the column was ready for testing. So we conducted tests on two columns the same time. The top one actually was not damaged. That was retrofitted from the beginning. The bottom one here shown to the right is damaged and then repaired and then tested. And we subjected both columns to a record, bi-directional record from the Loma Prieta earthquake. And I want you to watch here how both columns behave together. You will notice here that both columns were behaving almost identical. The capacity of the damaged column was restored. Its ductility was improved significantly just with 2 millimeter wires in a matter of 2.5 hours repair. So definitely that was a great successful test here, showing the potential of these materials for active confinement. Let us switch gears a little bit and talk about other important component in bridges, precast pre-stressed girders. One of the issues that's still lingering, honestly, when it comes to these precast components is the transfer of the pre-stress and the effect it has on the end region. We see in many cases, unfortunately, these end splitting cracks, especially in cross sections with skinny or thin webs and wider flanges where there's a lot of actually pre-stressing force transfer. There's been a lot of research in this area, so it's not new problem. There's no one quick 100% fix for it yet that satisfies everybody. When it comes to AASHTO or to PCI guidelines, they provide recommendations for using a lot of transverse reinforcement at the end region, which makes a lot of precasters unhappy, unfortunately. So we tried a new concept. Said, how about if we apply simply, transverse pre-stressing by throwing in couple end stirrups made of SMAs. So we tried this concept on a small scale specimens like this. Looks like an AASHTO type girder. And we only used one stirrup, number 2 stirrup made of SMA, 2 legs. And we found that we are able to apply a transverse pre-stress that reaches about 0.9 or so KSI, which our analysis showed that with this amount, we're able to almost eliminate all transverse cracks or splitting cracks that we see right there. We are actually going to be presenting on this topic at next month at the ASC Structures Congress, and we're now pursuing more testing to validate this concept. End region is not only a problem during pre-stress transfer. We see this all the time in existing bridges, actually due to the leaking of de-icing material or water through the joints, the bridge hinges. Now the question, should we replace the beam? Can we restore the capacity of the beam? DOTs and agencies, transportation agencies, are faced with these questions all the time. External pre-stressing is one of the great techniques for restoring capacity. However, for a tight region like this, it becomes very, very difficult because of the need for large equipment, hydraulic jacking equipment, and even anchorage blocks. So we came up with a very simple concept. It's called precast pre-stressing plate, the PPP concept, where we basically have a precast plate fabricated somewhere else and having a coil, if you will, of SMA that's pre-strained, not activated yet. You place it in that plate. You ship it to the site, you mount it or attach it to the surface of the concrete where it's needed repair or strengthening. For example, here it could be a web or it could be a flange. It could be a very tight region because really you don't need any anchorage block or system. Once it's ready, you apply the pre-stressing force by just simply heating the wire inside the plate. The pre-stress transfers to the substrate or the surface underneath. So we tried this concept with different variations or variants. This is one of the designs we came up with, which is the voided plate. So here you see 2 voids with the 4 SMA bars exposed. Part of the reason is that we wanted to inspect the bars during the heating process, but also we wanted to make heating it more easily. And then we mounted it on the block here to see how much of the pre-stress will transfer to that block. By the way, attaching the plate to the block or the girder could be using epoxy or mechanical anchorage or even a combination of both. When we activated the 4 wires, we found quite a bit of pre-stress transferring to the block underneath, and that was very great outcome. We even tested that block in flexure, as you can see, and the strength and ductility both improved tremendously, showing improved, behavior there because of the pre-stressing that's transferred. The most recent test we conducted was a large-scale test using this same concept with some variations in the concept. It's called the coupled pre-stressing plate, or the CPP. And this, I would say, the first test of that size, that scale, using SMAs that's done in the US. Basically, the idea is very simple. We have here 2 plates. They are not connected, but they are coupled with the SMA reinforcement that's running in between them. And these are precast plates. We can also supplement the reinforcement with some steel just to cut down on the cost of the material of the SMA. You simply attach these plates to the soffit, in this case of a PPC deck beam. Essentially, it's a box beam with some cracks in it, and we wanted to repair it, strengthen it, essentially. So here we used epoxy with some anchorage applied as well. And once it's ready, we just activated with the blowtorch, as I told you before. And in a matter of seconds, actually, the pre-stress is transferred to the bottom of the beam, and we were able to see cracks closing, and we were able to see an increase in the elastic capacity by over 50%. Amazing results. And I'm happy to share that we're going to be presenting on this during our TRANS-IPIC workshop next month. So it'll be a detailed presentation on that test next month. So I invite you all to attend. Let us switch to another transportation mode now, leave highway and move to railroads. They have their own set of issues and problems, especially when it comes to precast, pre-stressed concrete ties, like the ones I'm showing here, like end splitting crack problems, like center region cracking problems. So we started actually having discussions with experts in this area. Especially we started working with Rockla Concrete Tie, one of the leaders in developing these ties in North America. And we told them, how about if you eliminate the top layer of your, post-tensioning wires? That will help, of course, alleviate some of the stress at the end zones, which will help with the end splitting crack issue that they have. And then we could also add just localized pre-stressing using SMA bars just at the center region. We tried different configurations. We visited their plant in Florida for a couple of days, and we worked with them on implementing this technology in their ties. And once the concrete was cast and set, they shipped it to us for testing. It was very, very fruitful, an exciting experience we had with Rockla Concrete Tie. Now, the question that probably some of you might be wondering about is that, okay, now you have the SMA inside the concrete, everything is great, but how are you going to heat it up? The quick answer will be, well, we're going to have some, cables just connected to the SMA sticking out of the forms. And, when we need to heat it, we just connect it to a power supply and electrical resistivity will do its job, right? Yes, but we wanted something that is less complex and much simpler. And we thought about the induction heating. Some of you might be familiar with this technology. The idea is very simple. You have this coil that generates an electromagnetic field. And if a magnetic metal happens to exist in that field, then it will actually run a current in it, and that will heat up the material. So we're able, for example, just by scanning the top surface of this concrete block, to heat the bar inside and make it reach about 200 or 300 even degrees Celsius in a matter of few minutes. So that was an exciting technology that we wanted to explore in TRANS-IPIC. And what we did was basically we heated the SMA inside of these ties with this coil. And we were able not only that, but just by scanning the top surface of the concrete without even touching the SMA inside, to reach pre-stress at the top fiber as high as 1.61 KSI. Which resulted in a moment cracking capacity that exceeds even the ARIMA requirement. So that was very exciting thing to see here. The same concept could be applied for self-healing, something that we've been thinking about. There's been a lot of studies about in other areas, but now with SMA, imagine having something like this, a crack of this size, and you have SMA bars inside. Whether it's pre-stressed or not, if you heat it again, that's what happens. This is exactly specimen with SMA inside, and we heated the SMA. And, some of you might not even see where the crack is. And that, of course, will help in improving significantly the durability of concrete. So our group will be giving a talk next month also at the ASC Structures Congress in Phoenix about this health healing applications and research we've been doing with SMAs. The last thing I want to touch on, and I'm not going to spend much time because I know we're limited on time today, is design optimization using SMA pre-stressing. Now, in an era now where 3D printing and additive manufacturing is growing significantly, showing us how we can produce more efficient and optimized cross-sections that used to be very complex to produce, we thought about applying this to conventional bridge girders like AASHTO girders, for example. AASHTO type girders. So we conducted what we call a topology optimization process, where we basically remove the materials from locations where it's not needed that much, and keeping it where the stresses are high. So we end up with a quite complex geometry like this. Maybe with 3D printing, we can argue that we can now fabricate something like this more easily. However, the still problem is we have in these red zones you can see down there, those are highly tensile zones that we need pre-stressing. And with these zones being discrete like this, we cannot apply our conventional post-tensioning or pre-tensioning. But with the thermal pre-stressing, it's becoming more and more actually feasible now to pre-stress these localized regions. So we wanted to try something that's very simple, a simple optimization process, which the simplest form of that optimized shape would be a truss. So we performed some analysis on trusses. And yes, trusses are more popular in steel than concrete for obvious reasons, simply because tensile members in trusses would have to crack if it's made of concrete unless you pre-stress them, right? And pre-stressing each and every single one of them is a complex process. For example, in a truss like I'm showing here, the verticals are subjected to tension, so you would have to pre-stress each one of them. With thermal pre-stressing, that's possible. So we conducted this theoretical experiment, if you will, on a truss like this with only SMA placed in the verticals. The great finding was that we were able to achieve or meet the Ashton strength limit states while still cutting the amount of material by over 25% and the CO2 embodied, CO2 associated with the production of these materials. So there is potential there, no question about that, and we are now working on validating these results experimentally. In conclusion, I just want to say that SMA is a very exciting and new field that's emerging. It's a new material that we are not suggesting by any means replacing steel with, but supplementing reinforcement with it. Because as you can see from the examples I showed today, it could actually enhance the durability and resiliency of structures just by using small amount of the material at the right locations. The two exciting features of SMAs are the flat shape, the hysteresis, which is the superelasticity, and the shape memory effect, which we have been demonstrating how it could be used for thermal pre-stressing. As I said, this is a new field, and we're just scratching the surface here, and there is a lot of room for collaboration and for innovation. With that being said, I would like to, of course, acknowledge the funding that we received from various agencies supporting our research in SMAs. In particular, I thank, of course, the funding coming through TRANS-IPIC and the UTC program of the USDOT. Without this support and funding of the UTC, we are not able to take this technology to the next level or even doing large-scale testing and, of course, implementations, as you saw today. I can't end my presentation without, of course, thanking each and every single one of my former and current group members, from PhD students to postdocs who participated in, this work, and some of the work that's shown today, of course, without their help and collaboration, I would have never been able to achieve that. So with that being said, thank you again for your time and for your attendance. This is my email address. Please feel free to reach out to me anytime if you have any questions about SMAs or anything else we can chat about. And if we have time, I'll be more than happy to answer any questions.
Okay, great, thank you so much. I've been monitoring so far. I don't see any questions. If anybody would like to ask a question, you can type it into the Q&A. Oh, like, thought I saw a hand up for a second. We might have time for maybe one question if anybody has one. There we go. Can you see the question, Professor?
Yes, Chris. Let me read the question. What would happen for the SMA being subject to environment temperature? Very good question. That may affect the initial heat imposed on them. Very good question. Once the SMA, the way they behave is that once you hit a specific target temperature, it's called the austenite finish temperature. Even if there's fluctuation in the ambient temperature, and you're still within a certain range, which we have tested to be, for some alloys, could be up to maybe 70 or 80 degrees. then you have a very stable outcome. So basically, the temperature will have to drop to, for example, in the case of the alloy we're using, which is the nickel titanium niobium, has to go below negative 50 degrees to start seeing the pre-stress being lost. But other than that, they are very stable because of the wide thermal hysteresis, and that's another important factor. Of course, unfortunately, we don't have enough time to go through all these material-related properties, but some alloys actually would be very stable in this. Another question here. Chris, do we have time or?
We're a little bit short. I mean, if maybe one, I mean, I see there's two. Maybe you can answer one really quick, and then I think we should probably.
The hurdle, of course, cost is one big issue. Professor Zhang here, I see asked this question. And in my opinion, more than cost, because the cost depends on the demand. So the higher the demand, the lower the cost will be. So now the cost, we see it going down significantly compared to 15 years ago, for example, because there's higher demands now, and the demand is growing. But also the lack of knowledge. Sometimes we in civil engineering, we don't like to pursue things unless we are very comfortable with it. So really there should be more and more spreading of the knowledge about these new materials and how they could actually be implemented in civil engineering applications. Great question.
Great.
Thank you
so much. Yeah, I think we'll have to move on just based on time.
Okay, I'm going to stop sharing now.
Thanks everybody for your questions. Okay, so yeah, thanks very much, Professor Andrawes. I think we're ready to move on to the presentation from the research team at Purdue University. So today we have Dr. Chengcheng Tao, who is an assistant professor at the School of Construction Management Technology at Purdue University. Dr. Tao earned a PhD in civil engineering from the University of Florida. Prior to joining Purdue, Dr. Tao worked as an ORISE postdoctoral research fellow at the DOE National Energy Technology Laboratory. Dr. Tao's research interests include sustainable construction materials, manufacturing, mechanics of materials, and AI application in materials. Today we'll be presenting some interesting talk on data-driven smart composite reinforcement for precast concrete. So thanks very much for presenting for us. Take it away.
Thank you, Chris. Thank you, everyone. Good afternoon, everyone. My name is Chengcheng. I'm an assistant professor at Purdue University in the School of Construction Management. It's a great honor today to talk about my TRANS project, data-driven smart composite reinforcement for precast concrete. So here is the outline of my presentation. First, I'm going to introduce the motivation and objectives of our research, and then talk about 3 research components, including the development of smart sensor test bed for the composite reinforcement concrete and numerical modeling for the composite reinforced concrete, and also AI applications for the condition assessment, and then talk about the conclusions. So first, let's see the motivation of my research. As we all know, composite materials have been widely used in civil and construction industry. Composite rebars in concrete become much more popular now because of their higher strength, lighter weight, and high fracture toughness, long-term corrosions, and crack resistance. We can find different types of composite materials used for rebars, such as carbon fiber reinforced polymer, aramid fiber, basalt fiber, and glass fiber. And physical testing with trial and error approaches on the composite reinforced concrete materials usually take a lot of time, labor, and materials, especially when we want to monitor the condition of the material, detect failure and anomalies, and optimize the design of the system. So there is a lack of an efficient and accurate way to monitor and evaluate the condition of the composite reinforced concrete components. So my research objective here is I want to develop a smart composite reinforcement in precast concrete for real-time health condition monitoring. In order to achieve this goal, we have 3 research components. First, we want to develop a smart sensor-based test bed for the composite rebar in the concrete. And then we conduct the multivariate numerical modeling of the composite reinforced concrete. And third, we integrate the artificial intelligence algorithms to predict the real-time conditions and potential risks along with the reinforced concrete components system. And the diagram here shows the 3 research components, and I'm going to talk about them one by one. So the first task is the development of the smart sensor-based test bed. So here is the schematic of the test bed of the smart reinforced concrete beam. We applied 3 different sensors, smart sensors, including the embedded fiber optic sensor for the rebar, like here, the embedded fiber optic sensor for the composite rebar. And we have the micro measurement strain gauge attached on the rebar to measure the point strains as well. And we also have the extra long linear strain gauge for concrete to measure the strain of the concrete. And in addition to the smart sensors, we also have 4 image data collection devices, including the GoPro, cell phones, and drones, and also DIC cameras here. The design of the flexure test is based on the ASTM C293 standard with a total length of 20 inches and a span length of 18 inches. From the test bed, we are able to monitor and observe the material performance of the rebar and concrete in real time. So first, we started preparing the smart composite rebar by installing 2 types of sensors, like I just mentioned, the fiber optic sensors and the strain gauges. So the distributed fiber optic sensors can measure the strain along the entire rebar, while the strain gauge can only report the strain data at the points we put the strain gauges. So we install the rebar strain gauges next to the fiber optic sensors so that we can compare the result from the 2 sensors. Since the fiber optic sensor cable is very slim and delicate, so we need to have some way to protect the cables. So we have 2 ways here. The first one is we create a groove on the composite rebar, and we insert the silica tube in the groove and put the fiber optic sensor in the tube. And the second way is we use a thick layer of epoxy coating and attach the fiber optic sensor cable on the rebar using the epoxy coating to protect the fiber optic sensors. Before we put the smart rebar into the concrete, we want to make sure the sensors are installed well and the signals can be captured successfully. And then after the fiber optic sensors and strain gauges were installed, we made reinforced concrete beam samples using the mold. So we fixed the composite rebar using the rebar chair here before pouring the concrete. And we have some extra protection for the sensor cables at the edge area of the beam using the PVC tubes. After several days curing, we can demold the concrete beam. And in order to monitor the strain of the concrete, we also install another 2 strain gauges, concrete strain gauges, at the bottom area and the front area to collect the strain data from the concrete. So during the flexure test, we monitor the beam and collect the strain data of rebars and concrete using sensor interrogator here in real time, and record the images and videos of the beam using different cameras like a GoPro, cell phones, DIC cameras. Here you can see we plotted some grid lines on the beam because due to the configuration of our compression machine, the front area was blocked by the machine. So we can only record the videos and images from the side view. So we use those grid lines to do the conversion, the image conversion later. So here are the sensor data results collected from the fiber optic sensor and the strain gauge. We compared the strain data of the 2 rebars and the sensor data collected by the different sensors. Since we have 2 symmetric composite rebars in the bottom area of the concrete beam. So the sensors on the two rebars should provide the same values as you can see in the first two figures. And the strain measured by the fiber optic sensors matches quite well with the strain measured by the strain gauge at the same location as you can see in the third images. So the strain gauge and fiber optic sensors provided good results and captured the bending crack at the 300 second and the shear crack at 620 second. The results also matches with the load displacement data from the compression machine and videos. So as I mentioned earlier, we have two protection strategies for our fiber optic sensors, like we created a groove on the rebar. But we want to check if this groove will affect the performance of the composite rebar. So we compared the result of the rebar strain with the groove and without the groove, and we found that the two result matches quite well, and by comparing and analyzing the strain data on the rebar, we found the slim groove doesn't affect the strain too much, so we can put the silica tube in the groove to better protect the fiber optic sensors in the future. So in our current year 2 project, we aim to optimize the reinforced concrete components for better performance using the test bed developed from year 1. So we want to analyze more factors like the concrete fibers, water, type of rebar configuration of the system. Here is an example on the experimental study we are currently working. We want to check the effect of fibers and water on the concrete performance and workability. So according to the ACI 211 code, we conducted a series of slump tests on the concrete with different fibers and water content to determine their effect on concrete. And we will check more factors using more experimental studies this year and perform multi-objective optimizations on the reinforced concrete system. For the task 2, numerical modeling of the composite reinforced concrete. So the data provided by the physical testing is limited because it takes quite a long time to do each sample experiment. So we want to use a large data set for optimization and condition assessment. We definitely need to some complement ways to generate the data. So here we develop a multivariate numerical models in finite element analysis. We study the effect of 4 different composite rebars, including AFRP, BFRP, CFRP, and GFRP. We also check the effect of the concrete strength, like from 5,000 all the way to 22,000 PSI. And we also check the effect of the ribs on the rebar to see if they affect the mechanical performance. So the numerical models can be used to generate a larger data set to train our AI algorithms to predict and assess the condition and optimize the design. So here is the 3-dimensional finite element analysis result for the 3-point flexure test. The design of the flexure test is based on the ASTM C293 standard. For the FEA setup, we apply static general step and choose the concrete damage plasticity model to describe the concrete. And we also use different element types in the finite element models to describe the rebar ribs and its surrounding areas. From the finite element simulation, we could get a crack pattern like here showing the animation using the parameter called damage T. Damage T is short for damage intention. So the animation shows the finite element result for the flexure test, damage T on concrete, and also the stress on rebars over the time. After we finish the finite element analysis, we also validate our model result with experimental data. And as you can see in the pictures, at different time steps, the result between the finite element analysis and from the sensor data, they matches quite well, with a very high R-square value, more than 0.9. Through the experimental and the numerical investigation, we developed a digital twin model for the reinforced concrete beam system, and we can generate a big data set for AI-based condition assessment and optimization. So here are some more results, like using the finite element analysis to generate a larger data set by considering different rebar types from AFRP, BFRP, CFRP, and GFRP. We also change the concrete properties and also change the rebar ribs properties to generate a very large database. And in year 2, we aim to optimize the reinforced concrete design by searching a larger database. So we are expanding our material space by considering more factors like the rebar material. We use the steel rebar in addition to the composite rebar, and also we consider the steel stirrup inside the concrete beam and do more FEA simulations here. And you can see from the simulation result, the steel stirrups change the crack propagation patterns and reduce the vertical deflection and enhance the overall fracture resistant capacities. Also, we consider the effect of fibers in the concrete materials by changing different PVA fiber content in finite element analysis. With the increase of PVA fiber content, it reduces the vertical displacement and increase the concrete resistance to vertical fracture cracking. And in addition to the fracture test, we also conduct the pull-out test in finite element analysis according to the ASTM standard. We analyze the crack patterns from the pull-out test and compare our results with references. They matches quite well from this study. So from this simulation, it focuses on the bonding behavior of rebar and concrete using the dynamic explicit analysis. The modeling results were validated by the experiment from the references and can help us understand the bonding and cracking information between the concrete and the composite rebar. For the third task is AI-driven condition assessment for composite reinforced concrete. After we finish the first 2 tasks, we have data from experiment, from sensors, and also data from the finite element analysis. We also have image data captured by different cameras and image data from finite element analysis. We can combine, integrate all of the database and to use those database to train our AI algorithms to predict the condition for at different locations and at different time. So first, we trained different machine learning algorithms with our finite element analysis data to see which algorithm has a better performance. And we found that the tree-like algorithms had better performance than the linear algorithms. And among the 4 tree-like algorithms, the random forest regression gives the highest R-square value. So in the future training, we choose the random forest regression for our numerical and experimental data. So first, we want to predict the potential risk of the reinforced concrete beam on the 3-point bending test. As mentioned earlier, we use damage T data to represent the crack pattern and get the crack propagation over time. Here we apply the damage T data for the FEA to train the machine learning algorithm, and then the machine learning prediction matches quite well with the finite element analysis. From the machine learning model, we can predict the condition of the beam at different time and different locations and give a risk index maps accordingly. We also use the pull-out test data from finite element to train the machine learning and give a risk map for this pull-out test. And the R-square value is quite high, it's more than 0.9. As I mentioned earlier, because of the configuration of our compression machine, we cannot get the front view data, image data during the test. We can only get the side view data. So we plot some grid lines on the beam, and then we do the image processing before we train the images. So like here, we use some algorithm to convert the side image data to the front view image data. And after we got those algorithms done, we can use those images to train our machine learnings. And also, in addition to the images captured by the cameras, we also have images captured by the DICs, and we can integrate all of the images we have to train our deep learning algorithms. So here is an example how we use a deep learning algorithm to predict the performance of composite reinforced concrete system by training the image data. We trained the convolutional neural network algorithm to predict the strain in composite rebar using the crack images generated by FEA and also using the images captured by the cameras. We input them into the CNN network and output the maximum strain in the rebars. Here, we used two different CNN structures, LeanNet 5 and ResNet 34. So LeanNet 5 is a relatively small model which has 5 layers and more than 60,000 parameters. And the R square, you can see here for the first structure, the R square value is about 0.9. And then we also use ResNet 34. It's a bigger model which contains over 20 million parameters, and it generates a higher R square value for the strain prediction. So conclusions. So based on our progress so far, we have successfully developed a smart composite reinforcement in concrete beam. We have conducted multivariate numerical modeling for different rebars and concrete materials. We also trained different AI algorithms for the condition assessment using the data from smart sensors, cameras, and numerical analysis to predict the potential risk of the reinforced concrete system. In the future, we will consider more variables and configurations in the smart composite reinforced system and train the AI algorithm with a larger database. We will also do the multi-objective optimization for the reinforced concrete system for better performance like mechanical performance, sustainability, environmental performance, and also the cost. So here are our outcomes. So far, we have published one journal paper, and we have submitted 4 reports to TRANS-IPIC, 3 quarterly reports and 1 final report. We also presented our research outcome at the webinar last September and present our research at the workshop last year. In addition to those papers and presentations, my team also visited different concrete labs, like the lab in Alzinga and also the Army Corps lab last year, and get some material donations and also get some advice on our research project. Last but not least, I would like to thank the funding support from TRANS-IPIC and also thank the experimental support from North Dakota State University for the fiber optic sensor interrogator equipment. And thank every student in my lab. Thank you everyone for your attention. I'm happy to answer any questions.
Great, thank you so much. Let's see if there's any questions. I didn't see any come in while you were speaking, but maybe we'll see if we give people just a minute or two here to see if any questions pop up. Yeah, anybody has any questions? Feel free to type them into the Q&A. We can go through. Okay. So Professor Olek from Purdue,
Yeah.
I don't know if you can see this here. What is the length of your fibers that you're using?
Oh, let me see. I currently don't have the information about the fiber, but the name of the fiber is PVA fiber. It looks very slim and small.
And then there is an additional question from.
It's about 6 millimeters.
Oh.
Yeah.
Great. There's another question from the team at University of Buffalo. Are the results average from multiple sensors? Just wondering whether you can catch the peaks at cracks.
Yes, thank you for the question. We do a lot of different samples, and we use we put sensors. We put a couple of sensors on rebars, and we have several samples. We do the average, and we do the filtering on the sensor data. It can capture the peak at the cracks. So, like from our sensor data, it can capture the cracking pattern, which align well with our finite element analysis result. Yeah.
And there's just a clarifying comment asking about averaged over length. That averaged over length.
Over length, you mean over the beam length, or the?
I believe so.
We plot the sensor data along the beam, and I'm assuming there are multiple sensors in your fiber. Yes, we have so for the fiber optic sensor, it can capture the strain along the fiber, but for the strain gauge, it can only capture the point where we put the strain gauges. So for the fiber optic sensor along the fiber, we have 100,000 data points. So we do the average, we do the filtering on the data set. No worries. Thank you for the question. Yeah.
Great. Looks like that was the last question. So yeah, we're right at 1 p.m. So I think we'll probably call it there. Thank you so much for presenting. I just wanted to reiterate thanks to our presenters, Professor Andrawes and Professor Tao. Also wanted to note for everybody, just thanks for calling in and joining us for the March Research Highlights webinar. We'll have another webinar not in April, but in May. We'll be taking a month off for the webinar because, as I mentioned at the top, we have the in-person 2025 workshop in Chicago in April. So if anybody's interested in attending or finding out more about the workshop, you can find it on our website. And yeah, thanks everybody for calling in. Have a great day.
Thank you. Bye.
Thanks.